Long before we even had a concept of a power grid, the world's greatest engineers were stumped by a really fundamental challenge. How do you send mechanical energy across an entire city? So, let's dive into this incredible story of how London was powered not by electricity, but by water. I mean, really think about that. How do you power a whole city without a single electrical wire? This was the central question facing industrial London. The answer they came up with was just ingenious, revolutionary, and it all ran silently right beneath their feet. This is really a tale of two different networks, one born of ambition and another with immense city-altering power. So, the very first attempts to solve this problem started with the most obvious source of power in all of London, the incredible, unyielding energy of the River Thames itself. Way back in 1581, an engineer named Peter Moritz had this brilliant idea. He built these enormous water wheels right under the arches of London Bridge, using the fierce tides to pump water up into a tower. And from there, gravity just fed it into this sprawling, pretty primitive network of hollowed-out elm logs. This was, for all intents and purposes, the city's very first power grid. Now, what's so interesting here is the contrast. I mean, for the 16th century, this thing was a marvel. You're supplying thousands of homes with the river's free energy. But, and it's a big but, it was completely at the mercy of the tides. Plus, those wooden pipes and the super low pressure made the whole thing incredibly fragile. And this just perfectly illustrates the system's fatal flaw. During the Great Fire of London, people were frantically breaking open the pipes to get water, right? But all that did was cause the pressure to collapse completely, rendering the entire system useless right when it was needed the most. That catastrophic failure really set the stage for an even bigger problem. Because as the Industrial Revolution just roared to life, London's entire infrastructure was pushed way past its breaking point. It created a crisis on a scale that nobody had ever seen before. You have to try and picture the scene at the Port of London. It was absolute pandemonium. It was just choked with these massive steamships. Collisions were common, the docks were totally overwhelmed. And trying to power the cranes with individual steam engines, it was a nightmare. They were filthy, they were dangerously explosive, and they took up a ton of precious space. The city needed a new kind of power. Something clean, quiet, reliable, and available everywhere, pretty much on demand. The solution, it turns out, wouldn't come from above. It would come from a hidden world being built right under their feet. And this brings us to the main event, the London Hydraulic Power Company. This was a complete paradigm shift in how you could power a city. So instead of thousands of separate, dirty engines, the company used a few massive, centralized pumping stations. These stations pumped river water into a high-pressure, underground grid of tough cast iron and steel pipes. It was robust, it was centralized, and it was just incredibly powerful. And when I say powerful, I really mean it. The system maintained an absolutely astonishing 700 pounds per square inch of pressure, just constantly available across the entire network. This silent, totally invisible web of liquid power snaked its way across the city. It eventually spanned over 150 miles of underground piping, even crossing right under the Thames itself. At its absolute peak in the 1930s, the system was pumping over 32 million gallons of water every single week. It was the literal lifeblood of Victorian London. So what did all this water power? Well, pretty much everything. It drove the massive dock cranes, it ran the heavy printing presses for the newspapers, and it even powered the complex revolving stages at the London Palladium and those huge, heavy safety curtains at the Theatre Royal. It was the silent engine of the whole metropolis. But maybe the most profound legacy of this hydraulic network wasn't just about making things move horizontally. It was about allowing the city to finally grow vertically. I mean, think about it for a second. Before you had safe, reliable elevators, buildings rarely went higher than 4 or 5 stories. They were physically limited by human endurance. Who's going to rent an office or an apartment on the 8th floor if they have to climb all those stairs every single day? So here's the crucial point. It's this perfect chain of events. First, the hydraulic network provides this unrelenting citywide power. That leads to the widespread adoption of the powerful and, importantly, reliable hydraulic elevator. And once you have that, the human limit of 4 or 5 stories is just completely shattered. This is the moment the modern city skyline becomes possible. This one technology, all powered by this invisible grid of water, fundamentally severed that vertical constraint. It completely transformed the density, the real estate economics, and the iconic silhouette of London, and of course, cities all over the world. Okay, so picture this, London's Tower Bridge. It's one of the most iconic landmarks on the planet, right? Those massive arms, they're called bascules, each weigh more than 1,000 tons. But think about it, in an age of steam and steel, way before powerful electric motors, how on earth did they lift them so perfectly? Well, the answer is just a stroke of pure mechanical genius. But, to really get a handle on that genius, we've got to rewind a bit. Let's go back in time to what was then the dominant, but deeply flawed, power source of the early industrial age. So, for centuries, really, if you needed some serious muscle for your factory, your mine, or your textile mill, you turned to the water wheel. It was the prime mover, the engine of its day. But, and this is a big but, it was also seriously holding progress back. See, the problem was kind of threefold. First, water wheels were totally location-bound. You had to build your factory right on a fast-flowing river. But the real action, right? It was happening in bustling cities and ports. They were also super unreliable, completely at the mercy of droughts and freezes, when what industry desperately needed was consistent on-demand energy. And maybe worst of all, they were just incredibly inefficient. So, the solution? It came from a really unlikely source. On a fishing trip, a guy named William Armstrong is just watching a water wheel turn, and bam, he has this moment of insight that would literally spark a revolution in how we generate power. And look, Armstrong's idea, it wasn't just some small improvement. We're talking about a complete paradigm shift, a totally new way of thinking about how to create and use pressure. So who was this guy, William Armstrong? Well, he was actually a lawyer, a practicing solicitor, but he had this secret, obsessive passion for mechanical engineering. He looked at the world and saw that the future just couldn't be chained to the inefficient flow of a river. So in the 1840s, he does something pretty crazy. He takes this huge risk, abandons his legal career, and decides to chase his engineering vision full-time. Okay, so before Armstrong enters the picture, if you needed high-pressure water for your machinery, you really only had one option: brute force. Engineers had to build these absolutely monumental structures like the Grimsby Dock Tower, just to pump water high enough to create usable pressure way down at the bottom. They were astronomically expensive and incredibly limiting. But Armstrong's invention, well, it was about to change all of that. It was an idea so elegant and so powerful that it made these massive towers totally obsolete, practically overnight. It just completely reshaped the entire engineering landscape. What he came up with was, in essence, a massive mechanical battery. It was a device that finally unlocked the true potential of fluid power. It was called the hydraulic accumulator, and the principle behind it is just brilliant in its simplicity. You're storing energy, not chemically like in a battery today, but mechanically, by using water to lift an immense weight. Then, when you need that power, you just let the weight fall, and that forces the water out under absolutely incredible pressure. So let's break down how this thing actually works. Okay, first, a small steam pump slowly pushes water into this huge cylinder. As the water fills it, the pressure gradually raises this massive, super heavy plunger. Now, that raised weight is storing immense potential energy. When you're ready, you open a valve, and the sheer force of that weight coming down forces the water out, creating intense, perfectly regulated pressure to power any machine you hook it up to. And that right there, that was the breakthrough. All of a sudden, industry had this source of immense power that wasn't tied to a river, wasn't dependent on the weather, and was available the second you needed it. In one fell swoop, Armstrong's invention solved every single problem the old water wheel had.
And you gotta understand, this wasn't just some clever little gadget. Armstrong's invention became the invisible backbone of industry and infrastructure across the entire British Empire.
And man, you can just see how quickly this thing took off. From that fishing trip in 1835 to his first successful hydraulic cranes just 10 years later, the technology spread like wildfire. By 1869, you had dedicated accumulator towers, like the one at Limehouse in London, being built just to power entire districts. The applications were just staggering. It powered these silent, incredibly precise dockside cranes that completely transformed global shipping. It was the hidden muscle behind sophisticated new passenger lifts. Get this, Armstrong even used it at his own super high-tech estate, Craigside, to power a hydraulic rotisserie for his kitchen. I mean, how cool is that?
Which, of course, brings us right back to where we started, to that original mystery. How in the world did they lift those 1,000-ton arms on Tower Bridge? Well, for more than 80 years, the answer was a hidden array of William Armstrong's hydraulic accumulators, fed by steam-powered pumps deep within its foundations. These incredible mechanical batteries provided the silent, absolutely relentless force needed to raise and lower that bridge day in and day out. You know, it's really hard to overstate the impact of this. By creating a way to store and distribute massive amounts of power on demand, the hydraulic accumulator laid the critical groundwork for the kind of modern fluid power systems that are still absolutely essential to manufacturing all around the globe today. You know, when we think of the Industrial Revolution, the first thing that probably pops into your head is the steam engine, right? But what if the real story, the thing that truly kicked everything into high gear, wasn't just about making power, but about totally changing how we move it? We're about to dig into a really overlooked but absolutely crucial transition from total mechanical chaos to the precision of fluid power. This is the shift that really set the modern factory free. Okay, I want you to picture an early factory, and I mean really picture it. Forget everything you know about clean, organized assembly lines. This is a jungle. It's dark, it's deafeningly loud, and it is so dangerous. Dominating the whole scene is this massive, spinning steel shaft running the entire length of the ceiling, with leather belts slapping and whirring everywhere. That, my friends, was the line shaft, the absolute tyrant of early industry. It's kind of a crazy thought, isn't it? This incredibly dangerous, clunky system was somehow the very backbone of production. It was essential, but it was also deeply fundamentally broken. So how did we ever escape it? How did industry break free from this brutal reality? Well, the answer lies in a completely different way of thinking about power. To really appreciate just how big a deal the solution was, we first have to get our heads around the problem. So let's break down what made the line shaft such a tyrant. The whole logic was just brute force. You'd have one single gigantic engine, maybe a huge water wheel or a steam engine the size of a small house, and its only job was to spin one enormous steel rod. From there, every single machine in the entire building was physically chained to that one spinning shaft. The whole factory was basically a slave to this one engine. And as you can imagine, this created a whole cascade of problems. I mean, the system was just fundamentally flawed in 4 big ways. It was shockingly dangerous, it wasted a ridiculous amount of energy, it made a logical factory layout pretty much impossible, and it was incredibly fragile. Let's just talk about the waste for a second. Imagine you had to turn on every single light in your entire city just so you could read a book in your bedroom. That's basically the line shaft. This whole massive, sprawling network of heavy steel and leather had to be constantly grinding away, creating friction and noise, even if just one person was using one little machine. The amount of wasted energy was just astronomical. And this right here shows you just how illogical it all was. I mean, common sense would tell you to arrange your machines in the order of production, right? You know, an assembly line. But you couldn't. The line shaft forced you to put the machines that needed the most power closest to the engine, no matter where they fit in the workflow. It completely scrambled any chance of having a smooth, efficient process. And maybe the scariest part for a business owner, the whole system was a house of cards. The entire operation, hundreds of workers, hundreds of machines, all depended on this one system staying in one piece. If that main engine failed, or just one key belt snapped, it wasn't a small problem. The entire factory would just stop. Instantly, a deafening silence and production crashes to zero. It was the definition of a catastrophic single point of failure. So, industry desperately needed an escape hatch. It needed a way to deliver power that was flexible, efficient, and, wouldn't kill you. And the answer wasn't another machine at all. It was a fluid. Turns out, the solution had been hiding in plain sight for centuries, thanks to this principle from the physicist Blaise Pascal, way back in 1648. It's actually really simple, but it's also incredibly profound. If you pressurize a fluid in a sealed container, that pressure pushes out equally everywhere, all at once. Now, because liquids like water or oil don't really compress, they basically behave like solid rods of power. And I love how the source material puts it. They act as perfectly flexible, infinitely malleable rods of transmission. Just think about that. You can transmit immense force around corners, up a wall, anywhere you can run a pipe. And the new system was just beautiful in its simplicity. So instead of a giant engine inside the factory, you'd have a pump house, maybe in a totally separate building, just generating pressure. From there, you just run these small, flexible pipes to each machine. A worker just had to turn a single valve to get all the power they needed, instantly, only when they needed it and only where they needed it.
So look, this wasn't just some small upgrade. It was a complete paradigm shift. Bringing in hydraulics didn't just change the factory. It completely unchained it, freeing it from all those old physical limitations. I mean, the difference is just night and day when you put them side by side. Horrible inefficiency became power on demand. Extreme danger became safety because now the power source was somewhere else entirely. Illogical, rigid layouts gave way to flexible, logical assembly lines. And that scary single point of failure was replaced by a strong, decentralized network. Hydraulics won, on every single front. But here it is. This is the real revelation, the key idea that changed everything. For the very first time in history, the thing making the power was completely separate from the thing using the power. Factory managers no longer had to design their entire world around a giant spinning piece of metal. They were finally free to think logically. And the consequences of that freedom were immediate and just huge. Factories became dramatically safer places to work. Managers could finally lay out their machines based on the actual flow of materials, which is how we got the modern assembly line. This, right here, laid the true foundation for mass production and the explosive industrial growth that really defined the 20th century.
It's so easy to just overlook this quiet little revolution, but its legacy is absolutely everywhere. It's truly one of the invisible foundations that our modern industrial world was built on. And that is why this all matters so much. The decision to ditch that rigid, spinning shaft for a flexible, pressurized fluid, that wasn't just a minor improvement. It was the fundamental leap in thinking that made the scale, the safety, and the efficiency of the modern world possible.
All right, let's talk about something that powers nearly every heavy machine on the planet, but it's something you almost never, ever see. And no, I'm not just talking about oil. We're diving into the world of hydraulic fluid, the invisible, seriously high-tech blood that gives modern machinery its incredible strength. So, to really get where we are now, we have to travel back in time, back to the age of steam and iron. Picture this, a giant Victorian crane, all cast iron and rivets, lifting tons of cargo with hydraulic power. I mean, it looks absolutely invincible, but it had a hidden and often catastrophic weakness. So what was it?
Well, that secret weakness was the fluid itself. It was just plain old water. Now back then, using water to move giant machines was an absolute stroke of genius. But it came with some really big, inescapable flaws. Flaws that basically put a hard ceiling on how far the technology could go.
You see, water's basic properties made it surprisingly hostile to the very machines it was supposed to power. Think about a London winter. That water would freeze, expand, and just boom, catastrophically rupture those thick cast iron pipes. Or in a hot factory, it would actually boil inside the lines, creating these pockets of steam. That's called cavitation, and it would make the machines move in these dangerous, jerky lurches. And on top of all that, water is a terrible lubricant and an amazing way to make rust. It was literally eating the machines from the inside out.
But just as it seemed like technology was hitting a wall, a new hero showed up to solve all of water's problems. And this wasn't just a minor upgrade. No, this was a full-blown revolution that was about to unleash the true power of hydraulics.
So this huge shift happens right at the beginning of the 20th century. In 1905, two American engineers, Harvey Williams and Reynold Janney, they came up with the idea to replace water completely with mineral oil, derived from petroleum. And one of their first big tests? The massive, heavy-duty hydraulic systems used to turn the gun turrets on naval warships.
And let me tell you, the switch to mineral oil was an absolute game changer.
Why?
Well, for one, it had a way wider temperature range, so it wasn't going to freeze or boil. It's a natural lubricant, so it protected all those moving parts from grinding themselves into dust. And instead of causing rust, it actually prevented it. Just that one change allowed engineers to start designing machines that were faster, way more powerful, and could run at much higher pressures than they ever dreamed of before.
But of course, the story doesn't stop there. As the 20th century moves on, you've got the rise of aerospace, massive industrial machines, and the demands just got more and more extreme.
so extreme that even this revolutionary mineral oil started to show its limits.
The pressure started climbing into the thousands of psi, which generates a ton of heat. And under that kind of stress, basic mineral oil just thins out, losing its protective lubrication film. It would start to chemically break down, leaving these incredibly precise, expensive components totally unprotected from the huge forces trying to tear them apart.
This crisis really gave birth to the modern science of tribology, which is the study of friction and lubrication. Chemists and engineers, they realized they couldn't just use oil anymore. They had to design it. They started treating the base oil like a blank canvas, something they could infuse with, well, chemical superpowers.
So how'd they do it? I mean, how do you stop oil from getting thin when it gets hot? It's actually brilliant. Chemists added these long-chain polymers, things like polyisobutylene. You can think of them like millions of microscopic springs floating in the oil. When the oil is cold, they stay coiled up tight. But as the oil heats up and starts to thin out, these little springs physically uncoil and expand, which artificially beefs up the oil's thickness. It makes sure that protective film stays right where it's supposed to be. So clever.
Okay, but what happens when the pressure is just so insanely high that the oil film gets squeezed out completely? That's a state called boundary lubrication. And for a hydraulic system, this is the absolute nightmare scenario. We're talking direct metal-on-metal contact, which can completely destroy a component in seconds.
The solution to this problem is one of my favorite bits of chemistry. It's an additive called ZDDP, developed back in the 1940s. These molecules are like tiny chemical sentinels. The second they detect the intense, localized heat from metal-on-metal friction, they intentionally decompose and react with the steel surface. And they form, get ready for this, it's the technical term, a sacrificial solid glassy polyphosphate tribofilm. Basically, it's a super tough, solid glassy barrier that physically stops the metal surfaces from welding themselves together. I mean, how cool is that?
Okay, so the chemists had figured out how to handle extreme heat and extreme pressure. But there was still one enormous, deadly flaw with mineral oil that all this clever chemistry hadn't fixed. It's super flammable. And for the military and the brand new commercial aviation industry, this was a life-or-death problem.
This created a terrifying new question for engineers. If a high-pressure hydraulic line ruptures and sprays a fine mist of oil onto, say, a red-hot jet engine exhaust, what happens next? With mineral oil, the answer is not good.
Yeah, the outcome is a catastrophic fireball. So the industry needed something totally new, a fluid that was engineered from the ground up to just not burn, no matter what.
And they made it. In the late 1940s, Douglas Aircraft and Monsanto teamed up and created Skydro. This stuff wasn't based on petroleum at all. It was a completely synthetic fluid, built out of something called phosphate esters, a type of chemistry that has an incredibly high ignition temperature and just really resists burning.
Today, Skydro is, and I mean this literally, the lifeblood of commercial aviation. It's what powers the primary flight controls, the ailerons, the rudder. It's what moves the massive landing gear up and down. It runs the anti-lock brakes on pretty much every airliner made by Boeing and Airbus. And to help mechanics spot any leaks, it's given that famous distinctive purple or green color.
So, as we bring this all together, you can really see the incredible journey this technology has been on. It started as simple water, right? Then it became a refined oil, and finally, it evolved into this complex, synthetic, and totally purpose-built liquid machine component.
The key takeaway here is that the fluid is no longer just some passive stuff that transmits force. No way. It's now an active, highly engineered part of the machine. It's just as critical to that machine's survival and its performance as the hardened steel of the gears and the pistons themselves.
Let's talk about the hydraulic press. It's really the ultimate force multiplier. We're going to dive into how this incredible machine took a simple principle of physics and used it to, and I mean this literally, forge the heavy industry that built our entire modern world.
So how does it all work? I mean, how can a small, totally manageable push get transformed into a force that's powerful enough to move something absolutely colossal? It sounds like magic, but I promise you, it's pure physics.
Well, our story really kicks off back in 1795 with an English inventor named Joseph Bramah. He got a patent for a machine that took a scientific theory from the 1600s and turned it into this earth-shattering mechanical reality. It completely changed the game for what humans were capable of building. And the secret sauce? It all boils down to this core concept, Pascal's law. Basically, it says that if you have a fluid, like water, in a sealed container and you put pressure on it, that exact same pressure is felt equally everywhere inside that container. It doesn't get weaker or fade away at the other end.
So here's how Bramah Press brilliantly put that law into practice. A person pushes down on a small, narrow piston, right? That creates pressure in the fluid. That same pressure then pushes up on a much, much wider piston. And here's the kicker. Because that second piston has a way bigger surface area, the total upward force gets multiplied, like immensely. All of a sudden, a single person could lift weights that used to take whole teams of horses. But, for all of its theoretical brilliance, this revolutionary invention was almost a total bust. It had one critical, very practical, and very, very leaky flaw. See, the problem was the insane amount of pressure it was generating was too much for the technology they had at the time. The water would just blow right past any seal they tried to use, spraying violently out of the cylinders. And poof, all that incredible multiplied force would just vanish in a second, making the machine totally useless. And this right here just shows you the massive gap between the idea and the reality. On one hand, you've got Brahma's elegant, powerful, revolutionary concept. And on the other hand, well, you've got the actual materials of 18th century engineering. Seals made out of braided hemp soaked in animal fat. Yeah, they didn't stand a chance against that kind of force. So who saved the day? The solution came from a young, super smart mechanic working for Brahma named Henry Maudslay. And his idea? It wasn't just a fix, it was a stroke of pure engineering genius. Maudslay saw something everyone else was missing. He realized that trying to fight the pressure head-on, by just jamming more stuff into the gap, was a losing battle. He figured the seal needed to be dynamic, not static. It needed to work with the pressure, not against it. So here's what he came up with, the self-tightening U-cup seal. He designed this U-shaped collar out of leather and, this is the crucial part, he faced the open end into the pressurized fluid. As the pressure built up, it would get inside the U and physically force the leather lips outward against the cylinder walls, creating a perfect barrier. I mean, think about that for a second. Maudslay took the machine's biggest problem, all that insane internal pressure, and turned it into its biggest strength. The more pressure you applied, the harder the seal pushed back, making the connection even tighter. It was a perfect self-regulating system. And just like that, with this one brilliant fix, the true potential of the hydraulic press was finally unleashed. It wasn't just a machine anymore. It became the key that unlocked a whole new world for manufacturing and engineering. And boy, did it have an impact. The hydraulic press became the beating heart of industry, forging the components for trains that would cross continents, bending the thick steel armor for these powerful new navies, and forming the massive girders for the world's very first skyscrapers. Okay, so to really get your head around the legacy of what Brahma and Maudslay did, we gotta look at some of the really extreme stuff from the 20th century. This is where you see the true, astonishing scale of the force they made possible. Let's start with the RMS Titanic. A single person, the helmsman, could steer that 50,000-ton ship. Why? Because a small turn of the ship's wheel operated a hydraulic system that translated that tiny movement into enough force to turn the ship's massive, multi-ton rudder in the middle of the North Atlantic. Or how about this beast, the Bagger 288, one of the largest land vehicles ever built? This absolute monster of a machine relies completely on vast networks of hydraulic systems to move its staggering 13,500-ton frame and rotate its colossal cutting wheel. It's literally moving mountains of earth every single day. And this same idea could be used for just terrifying raw power. On World War II battleships, hydraulic rammers were used to shove 2,700-pound armor-piercing shells into the breeches of their main guns. That's a job that would be completely impossible for human strength alone. But here's what's maybe even more incredible. This same principle worked in reverse. When those city-leveling guns actually fired, the immense, violent recoil was safely absorbed by massive hydraulic cylinders. It proved that this technology could not only create unbelievable force, but it could also soak up the most destructive energies we could possibly unleash.
Okay, so look at this. On one side, you've got the Victorian era's best shot at fluid control, basically a leaky, rotting log. And on the other, a modern servo valve, machined to tolerances so small they're a fraction of a human hair. Now, they're both trying to do the same thing, but how we got from point A to point B, well, that's an absolutely incredible story of engineering.
The real game changer came in the 20th century. The demands of aviation and, frankly, World War II forced a revolution in materials science. All of a sudden, you have chemists engineering brand new synthetic rubber compounds. You can think of them as super rubbers, like nitrile and FKM. These things were designed, molecule by molecule, to resist nasty corrosive oils, handle insane temperatures, and stay flexible under just crushing pressure.
And all that research led to one of the most simple yet brilliant inventions ever, the O-ring. I know, it seems so obvious to us now, but this was the breakthrough. This one little synthetic ring finally let engineers create a perfect dynamic seal. We're talking about containing thousands of pounds of pressure without a single drop leaking. The struggle to contain power? It was pretty much over.
Okay, so containing the power, check. But that was only half the battle, right? The next huge challenge was controlling it. I mean, how do you direct all that incredible force with pinpoint precision, with speed, with reliability? This is what kicked off the quest for the perfect valve.
And guess what? Just like with the seals, the story of the valves is really a story of materials. Early valves, they were made of soft cast iron and bronze. They were heavy, they were slow, and high-pressure fluid would literally eat them away from the inside. So to survive, valves had to evolve. They started using forged steel bodies, and the internal parts were made of superalloys like stellite, a material so tough it's almost as hard as a diamond. That's a serious upgrade.
Now, the absolute heart of any modern hydraulic system is something called a spool valve. The concept itself is pretty simple. You have this highly polished metal cylinder, that's the spool, and it just slides back and forth inside a perfectly matched sleeve. But here's the magic. Those tiny movements are what direct massive amounts of fluid, and with it, enormous power. But this is where things get really tricky. It creates this microscopic dilemma. See, if the gap between that spool and its sleeve is even invisibly too large, the system leaks from the inside. You lose pressure, you lose control, but, and this is a big but, if the gap is too small, the slightest change in temperature or even a single tiny particle of dirt can cause the whole thing to seize up completely. The fit has to be, and I mean absolutely, perfect.
So, how do you get that perfect fit? Well, it meant moving beyond the limits of human skill. The solution was to enter a new realm of automated, microscopic perfection. It was nothing less than a revolution in manufacturing.
See, originally, making these was this agonizingly slow manual art called hand lapping. You'd have a master craftsman who would coat the parts in this fine diamond paste and then spend hours, sometimes even days, manually grinding the spool and the sleeve together until they fit perfectly. It was incredibly slow, inconsistent, and it meant that every single set was unique. No two parts were interchangeable.
But you can't build a modern Air Force with a bunch of artisans hand-grinding parts one at a time. This whole craft-based approach just couldn't keep up. When you need to control supersonic jets and guide missiles with split-second accuracy, you need a faster, more reliable, and completely repeatable process. The old ways, they had to be shattered.
And what replaced it was a whole new standard of precision. Today, computer-controlled machines can hit a tolerance of just 1.25 microns. Now, to give you some perspective on how insane that is, a single red blood cell is about 5 microns wide. So we're literally talking about manufacturing parts to a tolerance that is a fraction of the size of a single living cell. Just mind-blowing.
And the way they do it is through a process called match grinding. It's genius, really. A CNC machine uses a laser to measure the inside of the sleeve with incredible precision. Then, it automatically grinds the spool for a perfect fit every single time. It's a closed-loop system that just churns out flawless, interchangeable parts, all mass-produced with that sub-micron accuracy.
Okay, so with this brand new level of manufacturing precision, the stage was set for the final game-changing leap. This was the moment they could finally create a seamless link between the delicate world of electronics and the brute force world of hydraulics.
And the man who did it was an engineer named Bill Moog. In 1951, he created that link with his invention, the Electro-Hydraulic Servo Valve. And this little device, well, it was a technological marvel that was about to change the landscape of automation forever.
This is it. This is where everything we've talked about comes together. The servo valve takes a teeny tiny electrical signal, maybe from a pilot's joystick or a computer, and it uses that signal to move that perfectly machined spool we just talked about. And in an instant, that tiny little electronic pulse gets converted into a massive, bone-crushing hydraulic force. It is the ultimate bridge between a digital brain and pure physical muscle.
And once you know to look for it, you'll see the impact of this technology everywhere. I mean, from the steering gear of a massive supertanker to the boom of a construction crane. Without it, modern aviation would be literally impossible. Our cities would look completely different. You can think of it like this highly engineered fluid coursing through these precision ground steel arteries.
It really is the undisputed muscle silently holding up our entire global infrastructure.
If you watch old movies, you see these monstrous, clattering machines everywhere. But by the time you get to the 1970s, they're pretty much gone, vanished. So what happened? That's the big question we're tackling. And the answer, believe it or not, is all about the power of fluid.
Okay, so to really get why this was such a huge deal, you have to understand the crisis that came before it. Before hydraulics, the world was built by machines that were, well, to put it lightly, they were just brutal.
And this right here just nails the difference, doesn't it? On one side, you've got the old way, just clatter, constant danger, and sheer brute force. And on the other, the new way, that quiet hiss of fluid, incredible precision, and this almost elegant finesse. It wasn't just a small change, it was a complete flip of the script. The problem wasn't just that these old machines were clumsy, they were terrifyingly dangerous. I mean, operators were literally in a physical fight with their machines all day long. And those steel cables, they were like ticking time bombs. When one of those things snapped under tension, it turned into a metal whip that could cut a person in half. The physical toll from just the constant, violent jarring was enormous. Something had to give.
You get rid of that tangled, dangerous mess of cables and replace it all with something way simpler and 1,000 times more powerful, the hydraulic piston.
Let me walk you through this, because it's so elegant. Instead of slamming a clutch or yanking on some giant lever, an operator just nudges a little valve. That tiny movement sends pressurized oil shooting into a steel cylinder. The oil has nowhere else to go, so it pushes a piston out with this incredibly smooth, controllable, and absolutely unstoppable force. That's it. Simple, right?
Now, the really wild part is that this wasn't just one person's light bulb moment. Nope. All around the world, after the war, engineers were all struggling with the same exact problems, and amazingly, they all started landing on the same hydraulic solution at almost the same time. So let's do a quick world tour, and we'll start in France with a family-run business. These guys started out making gear for farms, but they ended up completely changing the face of construction in Europe. The Bataille family's company, Poquelin, put out the TU model back in 1951, and it was a total game changer. But the one everyone remembers, the one that became a true icon, was their 1960s model, the TY45. You couldn't miss it. That classic ruby red machine was absolutely everywhere during the European post-war boom. It became a symbol of a continent rebuilding itself with this amazing new tech. All right, now let's hop over the Atlantic to the United States, and the story here is totally different. It doesn't start in some giant corporation. It starts in a small garage in Ohio with two brilliant immigrant brothers. See, the Furwerder brothers had a problem. They needed to grade these steep roadsides, but all the manpower was gone, fighting in the war. So they invented their own solution, the Gradle. And its secret weapon was this unique telescopic boom. Since it was all hydraulic, it didn't need the massive overhead space a cable shovel did. It could reach under bridges, work around power lines. It had a level of precision that was just unimaginable before. And the name? Well, the name is just perfect. When Ray Ferwada's wife, Evelyn, saw the machine working, she said that. It really does capture that almost human-like control that hydraulics brought to these huge machines for the very first time. Okay, for our last stop on this global tour, we're heading to Japan. Over there, the massive job of rebuilding after the war kickstarted this huge leap in their own domestic engineering, and the company at the forefront was Hitachi. Hitachi's UH-03, which came out in 1965, was a real milestone. It wasn't just another machine, it was a huge point of pride, the first one developed completely using Japanese technology. And it had this super innovative two-pump hydraulic system. That basically gave the operator way more responsiveness and control. It made the machine faster, smoother, and much more efficient. So you've got these incredible pioneers pushing this technology forward in Europe, in America, and in Asia. For the old cable-driven machines, well, the writing was on the wall. It was game over. The new age of earth-moving had arrived, and the takeover was swift and absolute. I mean, why was it such a complete wipeout? Just look at the advantages. It was a total no-brainer. You could dig deeper, lift heavier loads, and work longer with way less maintenance. But the two biggest selling points, the real killers, were precision and, of course, safety. The age of that lethal snapping cable was finally over. Just stop and think about that for a second. In roughly 1 decade, maybe a little more, An entire class of machine that had built the world for half a century was made obsolete, gone. It was a complete and total revolution, all thanks to the quiet, unstoppable power of pressurized fluid.
The external gear pump. This thing is the invisible engine that literally carved the face of modern America. So that's the big question, right? How did this one relatively simple piece of engineering become so important that it literally enabled the largest public works project in human history? How did it completely reshape an entire continent? Well, let's get into it.
Okay, so our story kicks off in post-World War II America. The country was just booming, the economy was on fire, and there was this incredible sense of possibility in the air. But all that growth created a colossal challenge. How do you connect this vast, growing country? You see, the post-war boom meant cars were suddenly affordable for millions of Americans. And that created a huge, urgent demand for better roads. The answer finally came on June 29, 1956. That's when President Eisenhower signed the Federal Aid Highway Act, which greenlit an absolutely audacious goal to build a massive, brand new national highway system from scratch. And when I say massive, I mean the scale is just staggering to think about. The act gave the go-ahead for 41,000 miles of new multi-lane expressways. That's a network designed to crisscross the entire country, cutting through mountains, spanning valleys, and connecting every major city. It was an undertaking of truly epic proportions. But how do you even start to build something that big? I mean, to literally reshape the landscape on that scale, you need machinery that is unbelievably powerful. And that, right there, brings us to the technological core of our story, the hydraulic heart that powered the whole shebang. The bulldozers, the excavators, all the earth movers that built this system. The challenge was just immense. The construction industry needed machines that weren't just strong, but were absolutely relentless. They had to be able to work day in and day out in the dirtiest, toughest environments you can imagine, moving millions upon millions of tons of earth and rock. And the solution? It was the external gear pump. It's this beautifully simple mechanism that does one thing incredibly well. It takes the raw rotational power from a big diesel engine and transforms it into high-pressure fluid power. This is the very essence of hydraulics, using pressurized liquid to do incredible amounts of work. It's what gives a bulldozer the sheer force to literally move a mountain. People called it the beating heart of these new hydraulic behemoths, and that's exactly what it was. It just tirelessly pumped pressurized fluid, the machine's lifeblood, out to the hydraulic cylinders that move those giant blades, buckets, and arms with almost unimaginable force. So, how does this mechanical heart actually get the job done? Let's take a closer look at the elegant design of the pump itself. Its real genius is in just how simple and brutally effective it is. It all boils down to 4 simple steps. First, as the gear teeth pull apart on the intake side, they create a little pocket of low pressure, basically a vacuum. Second, that vacuum sucks hydraulic fluid from a tank right into the pump. Third, the fluid gets trapped in the gaps between the gear teeth and the pump's casing, and it gets carried around the outside. And finally, this is the magic part. As the gears mesh back together, that space just disappears, forcing the fluid out of the discharge port under incredible pressure. Now here's something that trips a lot of people up. You might think the fluid just squishes through the middle where the gears meet, right? Nope. That's a super common misconception. In reality, those interlocking teeth form a near-perfect seal, forcing all of that oil to take the long way around, and that is the key to building up all that pressure. Of course, engineers are never happy to leave well enough alone. The basic design was brilliant, for sure, but they knew it could be even better. So let's look at how they tweaked and refined it to make these pumps even tougher and more sophisticated.
The early pumps used what are called standard spur gears, the ones with straight teeth. They worked, but man, they were loud. The big innovation was moving to helical gears. Those have angled teeth that engage more gradually, which makes them run a lot quieter. Or, even better, the V-shaped herringbone gears. These not only run quietly, but they also perfectly balance out all the internal forces. And what that means is less wear and tear, a longer life, and more time on the job actually moving dirt.
So, okay, we've got this tough, super efficient little piece of technology. But what's the big picture? What did it all really mean? This is where we zoom out from the engineering details and see this small pump's absolutely world-changing impact. The power these pumps unleashed was almost biblical in scale. Seriously, with this technology, construction crews could do things that were unthinkable before.
They could flatten hills, carve out entire valleys for highways, dig the massive foundations for the skyscrapers that define our cities, and lift tons and tons of solid rock like it was nothing.
All this immense power was absolutely critical for meeting some very specific and kind of surprising design rules for the new highway system. For example, you ever wonder why highway overpasses are so high? Well, the Department of Defense mandated a minimum vertical clearance of 16 feet.
And the reason for that specific number? It's pure Cold War strategy. Get this, that 16-foot clearance was necessary to make sure the military could transport its largest hardware, including the enormous Atlas intercontinental ballistic missile, anywhere it needed to go. And lifting those huge concrete bridge decks into place required exactly the kind of extraordinary hydraulic force that only these pumps could provide. So you see, the external gear pump wasn't just another component, it was the fundamental enabler. Without the non-stop, high-pressure fluid power it provided, the rapid urban and suburban growth that basically defined the 20th century, it just wouldn't have been physically possible. The roads we drive on, the buildings we work in, so much of it exists because of this simple pump.
So you gotta ask, right? How on earth did the power of that get inside of this? How did we go from these colossal, building-sized machines to the powerful, mobile equipment we see everywhere today? To answer that, we've got to go back in time, to an era when hydraulic power was an absolute titan, but a titan that was completely chained down.
So, back in the late 1800s and early 1900s, hydraulic power was this industrial giant. I mean, it was the force in industry, but it had one massive problem. It couldn't leave the building. It was powerful, sure, but portable? Not a chance.
I mean, look at this. These early systems were built on a massive scale. They relied on room-sized steam engines, used plain old water, and were made of super heavy cast iron. The whole setup took up entire buildings. They had incredible force, yeah, great for forging steel, but because they were so huge, they were totally impractical for anything that needed to move. The idea of putting all that power on wheels, it sounded like something straight out of science fiction.
So the challenge was crystal clear. How do you shrink all that immense power without actually losing any of it? This was a monumental engineering puzzle. It needed a real visionary, a fresh perspective. And it found one. But it came from a very, very unlikely place. From a guy with a brilliant, hands-on kind of mind. Okay, so who's our hero? The guy who finally set hydraulics free was named Harry Franklin Vickers. He was a self-taught mechanic, and today, yeah, he's celebrated as the father of industrial hydraulics.
And what's so wild is that Vickers didn't have a formal engineering degree. He just had this brilliant, natural understanding of how machines and fluids worked. His path was super unconventional for sure, but it led him straight to a breakthrough that would change, well, pretty much everything.
And this is where the story gets really good. It's like something out of a movie. He had this chance encounter, repairing a fishing reel, of all things, for the famous Western novelist Zane Grey. And Grey was just blown away by his mind. He saw this spark of genius and actually paid for professors to tutor Vickers. This gave Harry the advanced, high-level knowledge he needed to tackle the really big problems.
So now, armed with all this new knowledge, Vickers zeroed in on the real heart of the problem, something called power density. Basically, it's just the amount of power you can cram into a certain amount of space. He knew that for hydraulics to ever go mobile, the parts had to get way, way smaller, but at the same time become way, way more powerful.
And that focus on power density led him to his masterpiece, his crowning achievement. It was a totally revolutionary invention that solved the single biggest, most destructive problem that plagued every hydraulic pump at the time, an issue where they were literally destroying themselves. Okay, so check this out, because this really lays out the engineering challenge. The old pumps were just tearing themselves apart from the inside. The high-pressure fluid would push the spinning part, the rotor, sideways with tremendous force. This caused crazy amounts of wear on the bearings, and it seriously limited how much pressure and speed you could get out of them. But Vickers' solution? Oh, it was just pure elegance. His design created two pressure zones on opposite sides of that rotor. So you had this high-pressure area on one side that was perfectly canceled out by an equal high-pressure area on the other.
And the result of this? It was a total game changer. All of a sudden, engineers had the one key piece they'd been missing all along: a compact, super durable, high-pressure pump. This was going to be the heart for all kinds of powerful, mobile hydraulic systems.
But here's the thing, it wasn't just about one man or one invention. As critical as Vickers' breakthrough was, it was actually part of a much bigger wave of innovation that was all happening at the same time.
You had all these other things going on that were absolutely crucial. Other kinds of pumps, like axial piston pumps, were getting perfected for super high pressures. We got new high-strength steel alloys to replace that old heavy cast iron. Machining got so much more precise, which cut down on leaks and made everything more efficient. And, maybe most importantly, we finally got steel-braided flexible hoses to replace rigid iron pipes. For the first time ever, you could actually send that fluid power to moving parts, like the arm of an excavator.
So, when you put it all together, Vickers' balanced pump, the new materials, the precision manufacturing, the flexible hoses, engineers could finally do what everyone thought was impossible.
Yeah, this was the magic formula. You shrink the components, but you scale up the pressure. That combination is what finally untethered fluid power from the factory. It was free to roam the earth.
And for his huge, monumental role in this whole revolution, Harry Vickers got the ASME medal back in 1956. And that's no small thing. It's the highest honor you can get from the American Society of Mechanical Engineers. It's just a real testament to how massive his impact was.
Today, we're diving into a revolution in aviation that's pretty much invisible, but absolutely essential. It's the story of how engineers decided to just squeeze harder, taking a giant leap in hydraulic pressure that, believe it or not, is what allowed the biggest passenger planes ever built to even get off the ground.
So, let's start with a question that sounds more like a riddle, right? How in the world do you make a 500-ton airplane lighter? It seems totally impossible. But the answer isn't about what you remove. It's all about how you apply force. Here's how we're going to break it down. We'll look at the old standard that worked for decades, the huge problem that finally broke it, the simple, elegant physics that solved it, the incredible chain reaction of savings that came next, and of course, the new stuff that had to be invented to make it all work.
Okay, first things first. We have to understand the world before all this happened. For about half a century, a single number ruled the world of aircraft hydraulics. 3,000 psi. It was the undisputed king.
And before we get into the nitty-gritty, we have to remember the golden rule of aerospace engineering. Weight is the ultimate enemy. Every single extra pound costs fuel, it cuts down your range, and it eats into an airline's profits. The whole game is a constant battle against gravity. Back in the 1950s, engineers found what they thought was the absolute perfect balance. 3,000 pounds per square inch was the most pressure that the lightweight aluminum alloys of the day could handle without, failing catastrophically. This became the sweet spot. It gave them enough power to control the jets of that era without having to use stronger, much heavier metals.
But then, right around the turn of the century, a completely new kind of aircraft showed up. And that sweet spot, well, it turned sour fast. The sheer size of these new planes created a super jumbo-sized problem.
We are talking, of course, about the absolute giants of the sky, the double-decker Airbus A380 and the game-changing Boeing 787 Dreamliner. These things weren't just a little bigger. Their scale fundamentally shattered the old engineering models.
Just look at this number, 22.5 tons. That's the amount of aerodynamic force pushing on a single rudder of an A380 when it's in flight. To put that in perspective, that's like trying to move a giant door with 4 huge elephants leaning against it, and you have to do it instantly.
This quote really says it all. The engineers weren't just dealing with planes anymore, they were dealing with flying leviathans. The old math, the old rules, none of it worked. They had to come up with something completely new.
Think about it. If they had just stuck with the old 3,000 psi system, the A380 would have needed gigantic hydraulic pumps and these massive, thick hoses running from nose to tail. The weight of that system alone would have been a crippling penalty, basically making the plane a financial failure before it ever flew. They had to get the exact same power, but with way, way less weight.
And that brings us to the solution. And what's so cool is that it wasn't some crazy, exotic, new technology. It was a really clever and, frankly, bold application of a basic law of physics. It was a true aha moment.
The secret is right here in this simple equation. The power you get out of a hydraulic system is just its pressure multiplied by its flow rate. So if you need a certain amount of power, you have 2 choices. You can move a lot of fluid at low pressure, or you can move just a little bit of fluid at a very high pressure. And here's what that choice looks like in the real world. By cranking the pressure up by more than 60% to 5,000 psi, the engineers got the exact same amount of power, but they only needed to move 42 gallons of fluid per minute instead of 70. That is a massive 40% reduction in flow.
And here's where it gets really amazing. That 40% reduction, that wasn't the end of the story. It was just the first domino to fall. It kicked off a chain reaction, a cascade of weight savings that rippled through the entire plane.
The logic here is just so beautifully simple. You've got higher pressure, so you need less fluid. You need less fluid, so you can use smaller pumps to move it. And if you have less fluid moving through smaller pumps, well, you can use much smaller, thinner pipes everywhere.
And these weren't tiny savings. The pumps themselves got 20% lighter. Hoses that would have needed to be 3 inches thick could now be just 2 inches thick. Now imagine that reduction multiplied across miles and miles of tubing and hundreds of fittings and manifolds snaking through the fuselage and wings. The weight just starts to vanish.
So, what was the grand total? All that downsizing added up to this: a mind-boggling 2,500 pounds. That's more than a ton of weight saved on the A380, just from squeezing the fluid harder. That is literally like taking a small car out of the plane's empty weight. Just a monumental achievement.
But of course, there was a catch. This kind of power comes at a price. Containing 5,000 psi is a serious challenge. It meant they had to completely rethink the materials they used to build the system. The old rules and the old reliable metals were toast.
Here's the trade-off they were facing. Aluminum, the go-to for the old 3,000 psi systems, would just violently rupture under 5,000 psi. No way. The only real options were super strong titanium and advanced steel alloys. Now the problem is, those metals are a lot denser than aluminum. But, and this is the key, because all the components were now so much smaller, that density penalty was totally wiped out, and they still ended up with a huge net weight saving.
And you know, they weren't just guessing that this would work. This technology had already been battle-tested. The aerospace industry had already perfected 5,000 psi systems for military aircraft like the F-18 fighter jet and the V-22 Osprey tilt rotor. That military experience is what gave them the confidence to take this leap in the commercial world.
You know, every time you get on a plane, you're trusting this invisible, life-saving network that's hidden away inside the wings and the fuselage. It's a system that's literally designed to think, to react, and to survive when everything, and I mean everything, goes catastrophically wrong. Today, we're digging into this aircraft nervous system and how its brilliant design saved 469 lives during one of the most intense emergencies in aviation history. Let's get into it. So our story kicks off on November 4th, 2010. Qantas Flight 32, this massive Airbus A380, has just lifted off from Singapore. It's supposed to be just another routine flight, but in just a few minutes, it's going to become the textbook case for surviving against completely impossible odds. Just 4 minutes out from the airport, bam, a massive explosion. And this wasn't just a simple engine failure, it was an uncontained failure. That means the number 2 engine basically shredded itself, sending a hurricane of red-hot metal tearing right through the wing. Instantly, the cockpit just lights up with this overwhelming waterfall of error messages. The pilots aren't dealing with one problem here. They're facing dozens of critical system failures, all at the same time. The sheer scale of the damage here is, well, it's staggering. I mean, this is way beyond what engineers even plan for in their worst-case scenarios. The shrapnel from that engine didn't just punch a few holes. It severed the aircraft's vital arteries and nerves. It crippled hydraulic systems, it tore into fuel systems, and it sliced through about 650 electrical wires. The plane was literally bleeding out, both hydraulically and electronically. And that brings us to the big question, right? With its wing looking like Swiss cheese and its systems just screaming in chaos, how on earth did this colossal airplane not just fall out of the sky? Well, the answer isn't luck. It's in a deep core philosophy of design that expects disaster and builds in layers upon layers of protection. A philosophy we can think of as creating a body with redundant muscles. Yeah, this survival story, it wasn't a fluke. It was all about a deliberate, uncompromising engineering philosophy. The goal is to make the aircraft as resilient as a living thing, something that can take a massive hit and just keep on going. And it all starts with hunting down and eliminating one very specific vulnerability. And that vulnerability is the single point of failure. The absolute #1 mission of aviation engineering is to make sure that no single event, no matter how bad, can ever doom the entire aircraft. If one system gets knocked out, another one has to be right there, ready to take its place, instantly and automatically. To really get this, let's talk about the plane's muscles, the hydraulic system. See, when a pilot moves the controls, they're not physically wrestling with those giant flaps on the wings. No way.
They're sending signals that tell the hydraulic system to apply immense force against the wind. If you lose this system, you lose control. Period. Game over. So, how do you protect it? Well, you don't build one super strong system, you build several totally independent ones. Early planes, they had one hydraulic circuit, a classic single point of failure. Then the industry standard became 3 separate circuits. But the A380 on Qantas 32 had something even more advanced, a 2H2E architecture. That stands for 2 hydraulic and 2 electrical backup systems. This deep redundancy was key, but just having multiple systems is only half the story. You have to protect them from each other. And this is where a really clever idea called spatial segregation comes into play. The designers literally route the tubes and the wires for these backup systems through completely different parts of the plane. They're kept far apart. So when that engine shrapnel tore through one part of the wing on Qantas 32, it couldn't possibly sever all the control lines at once. There was always another path, located somewhere else, safe and sound, ready to carry the pilot's commands. Okay, but what happens when one of those systems gets damaged and starts losing pressure? The healthy systems need to step in and help, but that creates a huge danger. And this is where we see a truly ingenious mechanical reflex kick in. So here's the dilemma. You absolutely need to use a healthy system to power a damaged one. But if that damaged system has a leak and you just start pumping your good hydraulic fluid into it, you're just gonna pump it all overboard, into the sky. You drain the healthy system, killing them both and dooming the plane. So the solution is this. You have to share the power, but not the fluid.
The solution is this beautiful piece of engineering called the Power Transfer Unit, or PTU. You can think of it like a mechanical translator. It takes the pressure from a healthy system, let's call it the yellow one, and uses that pressure to drive a motor. That motor is connected by a shaft to a pump inside the damaged system, say the green one. And that pump repressurizes the green system's own fluid, bringing it back to life. Not a single drop of fluid is ever exchanged between them. It's brilliant.
And here's something amazing. If you've ever flown on an Airbus A320, you have probably heard this system working. You know that weird barking dog or kind of groaning sound you sometimes hear from under the floor after you land or while you're taxiing? That's the PTU. It's just running a self-test. It is not a sign of a problem. It's the sound of one of the most critical safety systems on the plane, making sure it's ready to save you. So, we've got redundant muscles and these ingenious reflexes, but none of that matters if the aircraft's brain, the flight control computer, is being fed bad information. And this brings us from the plane's muscles to its brain. Modern jets are fly-by-wire. All that means is computers translate what the pilot does into action. To do their job, they rely on tons of sensors measuring things like airspeed and angle. But what happens when a sensor fails, or it gets iced over, or it just starts spitting out garbage data? How does the brain find the truth in all that chaos?
Well, this chart shows a really simple but potentially fatal flaw in logic. Your first instinct might be to just average the readings from 3 different sensors, but look what happens. If 2 sensors are reading normally, say 10 and 11 degrees, but a faulty third one is suddenly screaming 90 degrees, well, the average becomes 37 degrees. And that is a wildly incorrect, dangerous number to fly with. Acting on that could be catastrophic.
So instead, engineers use this lightning-fast digital reflex called the mid-value select algorithm. The logic is so simple, it's brilliant. The computer looks at all 3 values, 10, 11, and 90, and it doesn't average them. It just instantly throws out the highest value and the lowest value, and it uses the one that's left in the middle, in this case, 11 degrees. It finds the truth by totally ignoring the lie. This makes sure the hydraulic muscles only ever react to pure, accurate data. So how did all this come together? Let's go back to the cockpit of Qantas 32, as the crew is desperately trying to land a crippled giant that is barely flyable. I mean, the list of what wasn't working is just mind-boggling. The autopilot was out, most of their brakes were gone, the speed brakes on the wing, gone. The plane was over 50 tons overweight with fuel they couldn't dump, and the computers were actually telling them their landing configuration was impossible. By all accounts, they were facing a completely unlandable situation. But, and this is the whole point, despite the hundreds of failures, the pilots had a plane they could actually fly. Why? Because the spatial segregation of that 2H2E architecture meant not all the lines were cut. Because the PTUs were busy sharing power between the systems that were still alive. And because that mid-value select logic was constantly filtering out bad data. The fail-safe design gave the crew a fighting chance. On board that aircraft were 469 human beings.
And thanks to some of the most masterful flying you'll ever see and a brilliantly resilient machine, the number of injuries was 0. Yeah, the final report didn't just call it a safe landing. It was deemed an absolute triumph of fail-safe design. It was living proof that this complex, hidden nervous system, built on decades of hard-earned lessons, works exactly like it's supposed to in the absolute darkest of moments.
You know, to really understand why this new tech is so revolutionary, we first have to take a look at the old way of doing things. For decades, there was a system that was like the powerful but really, really heavy heart of every single large aircraft.
For the longest time, planes relied on something called a central hydraulic system. Just imagine a single massive heart, right? And it's just pumping hydraulic fluid through miles and miles of tubing. Think of them like arteries, all over the plane to move things like the rudder and the flaps. I mean, it was a powerful system for sure, but as we're about to see, it was also unbelievably inefficient.
Yeah, this old-school approach is known as fluid by wire. And boy, did it come with some major baggage. We're talking miles of heavy metal pipes crisscrossing the airplane. There was a constant risk of tiny, microscopic leaks that are an absolute nightmare to track down. It put a huge power drain on the engines. And the maintenance? Oh, it was just incredibly complex.
So here's the bottom line. This old guard of flight control was just incredibly clunky. The weight alone was a massive penalty when it came to fuel efficiency. The maintenance was a constant headache, and because those pumps were always running, they were just continuously bleeding energy from the engines, even when the plane was just flying straight and level, doing nothing.
But of course, engineers knew there had to be a better way, right? And this search led to a complete revolution in the technology that actually moves the control surfaces, a revolution that basically threw out the old playbook entirely. So, let's meet the hero of our story, the Electro-Hydraulic Actuator, or EHA for short. Now, instead of one giant central heart, I want you to imagine every muscle in the plane having its own tiny, super powerful heart. An EHA is this self-contained little unit. It's a perfect blend of mechanics and electronics, and it creates hydraulic power right at the spot where it's needed, like right on the hinge of a wing flap.
And this new way of thinking, it's called power by wire. Instead of all those heavy, leaky hydraulic lines, it uses simple, lightweight electrical wires. This just gets rid of miles of vulnerable tubing. It makes the whole system way less likely to get damaged. And, this is the big one, it only uses power when it's actually needed.
And you know, that last point is the absolute game changer here. This whole idea of power on demand is exactly what makes the EIHA so unbelievably efficient. So, let's dive in and see how it actually works.
Inside each one of these EHAs, you've got the whole shebang packed into one neat little unit. There's a powerful electric motor, its own dedicated pump, a very small amount of hydraulic fluid in a tiny little reservoir, and the cylinder that does all the pushing and pulling. It's really a little masterpiece of mechatronic design.
Now, think back to that old system, remember? Its pumps were physically connected to the engines, which meant they had to run constantly for the entire flight just to keep those hydraulic lines pressurized and ready to go. This wasted just a colossal amount of fuel and energy.
Now, contrast that with the EHA. Its electric motor just sits there, perfectly still, consuming absolutely zero energy until the second the pilot or the autopilot commands a move. Then, whoosh, in a fraction of a second, it spins up, does its job, and goes right back to sleep. The energy savings are just immense.
But you know, this brilliant mechanical design, it's really only half the story. The real magic, the secret sauce that unlocks its true potential, is in the software that controls it, the brains behind the brawn.
So that brings us to the next big challenge, right? You've got this incredibly powerful and super responsive device. How do you actually control it with the kind of precision you need to guide a massive airplane through the sky? Well, the answer lies in some very, very clever code.
So for a long time, engineers used something called a PID controller. It's pretty simple, and it works great for predictable linear tasks. Think of it like cruise control, keeping your car at a steady speed on a perfectly flat, straight road. But fluid dynamics, they're unpredictable. It's more like driving on a bumpy, winding mountain pass. A PID controller just can't keep up. It can overshoot the target or cause vibrations. And that's why modern systems use something way more advanced, fuzzy logic controllers.
Fuzzy logic is just brilliant because it doesn't really rely on rigid math.
It actually allows the actuator to think and adapt to all these unpredictable situations, like a sudden gust of wind hitting the wing. It can literally predict and cancel out pressure spikes before they even have a chance to affect the control surface. It's proactive, not reactive. It's a huge deal.
So what does all this fancy software actually get you? Well, simulations and research have shown that these fuzzy logic algorithms can improve control performance and precision by up to 99% compared to the older methods. Let that sink in. 99%. That is just a staggering leap in capability.
So when you put it all together, you've got the elegant hardware and this brilliant software. What you get is the definitive future of how we control aircraft. It's as simple as that.
So what's the final payoff here? What does this all mean? Well, EHAs deliver massive energy savings, and that leads to lighter, more fuel-efficient airplanes. They give pilots lightning-fast response times with absolutely zero sluggishness. They completely get rid of that target overshoot problem and provide what engineers themselves call buttery smooth control. You know, as we push further and further out into space, we keep running into this one fundamental, totally unforgiving enemy. And to beat it, we're not just building rockets a little differently, we're completely rewriting the rules of how things are made. This is the story of how we're finally conquering mass.
Look, in the world of rocketry, this isn't just some catchy phrase. It's the law. Every single gram you add to a rocket fights you. Every single inch of the way to orbit. There's just no room for waste. Absolutely no margin for error.
So why is mass such a brutal enemy? Well, it all boils down to something called the rocket equation. And it's a really cruel bit of physics. To lift just 1 extra kilogram of a part, you don't just add 1 kilogram of fuel. Nope. You have to add an exponentially compounding amount of heavy propellant just to break free of Earth's gravity. It's a tyrant.
To really get what a game changer all this new tech is, we first have to look back at the old way of doing things. For decades, making critical rocket parts was a strictly subtractive process, meaning you start with something huge and just carve your way down.
The process was pure brute force. A machinist would take this giant solid block of metal, like steel or titanium, and use these huge drills to bore a network of tunnels inside. This would create a part called a manifold, which basically directs fluid. But because a drill can only go in a straight line, this seemingly simple approach had some serious hidden flaws.
So what you ended up with was this jagged maze of sharp 90-degree angles. Now when high-pressure fluid smashes into those corners, you get massive turbulence and friction, which forces the engineers to use heavier, more powerful pumps just to compensate. And even worse, all those entry holes had to be sealed with these heavy plugs, adding useless dead weight and creating dozens of potential points for a catastrophic failure. The old way was just heavy, inefficient, and honestly, pretty risky.
But now, in the modern aerospace world, led by pioneers like SpaceX, that old method has been completely thrown out. They've embraced a revolutionary new way of doing things: metal additive manufacturing, or what we all just call 3D printing.
And just look at the difference when you put the two philosophies side by side. For a part like a manifold, which is kind of like the heart's arteries for an engine, it is night and day. Instead of carving away from a solid block, you build up from nothing. Instead of jagged right angles, you get to create smooth organic curves. And instead of adding heavy plugs, you get a seamless, incredibly lightweight part.
So how does this magic actually work? Well, using these really advanced machines from partners like Velo3D, a process called laser beam powder bed fusion gets going. A blade spreads an incredibly fine layer of metal powder, almost like a snowfall. Then, these high-powered lasers instantly melt and micro-weld that powder exactly where it's needed. The part is literally built atom by atom from the ground up.
And here's the true magic of this whole process. What it unlocks is this idea of unconstrained geometric freedom. Designers are no longer trapped by the straight line of a drill bit. They can design these internal channels that look more like the arteries in a living creature, perfectly optimized, curved, and efficient. All that violent turbulence and pressure loss? Gone.
Now, a huge historical challenge for metal printing was that any parts that hung over could just collapse during the print. But modern software is so smart, it intelligently adjusts the laser power and speed second by second, and these special non-contact blades snowfall the powder instead of scraping it. This lets them print massive, hollow channels with almost perfectly horizontal overhangs without any internal supports, which is key to keeping those fluid paths completely clear. Okay, so this isn't just some cool theory. The results in the real world are absolutely staggering. And there is no better proof of this than the aggressive, rapid evolution of the SpaceX Raptor engine. And here it is. This is the payoff.
By hollowing out all that unnecessary bulk and optimizing the structure, these new additively manufactured parts achieve a verified weight reduction of up to 70%. That's not an improvement, that is a monumental leap forward.
Let's take the engine itself. The early Raptor 1 was a marvel, for sure, but visually, it was chaotic. It was this heavy mess, a spaghetti of external pipes, cooling circuits, and other flow paths all bolted onto the outside.
Raptor 2 showed some really aggressive improvement. You could see the design was getting cleaner, way simpler, but it was still burdened by all that external plumbing, which, just adds weight and complexity.
And then came Raptor 3. Aerodynamically, it is perfectly clean. So what happened to all that spaghetti? The SpaceX engineers printed it directly into the structural walls of the engine itself. The complexity didn't just get rearranged, it literally disappeared from sight.
And the benefits here are just compounding. By moving all that plumbing inside, you get to eliminate the heavy external heat shields. You remove all those complex and heavy bolted connections. You can even get rid of entire fire suppression systems. The result is just a massively lighter and way more reliable engine.
So the Raptor 3 weighs just over 1,500 kilograms, but it generates a staggering 280 tons of thrust. I mean, that incredible power-to-weight ratio is a direct result of this relentless, additive-driven war on mass.
And this whole philosophy of shedding mass didn't just stop at the engine. Oh no, it extended to the systems that steer the entire rocket, what's called the Thrust Vector Control, or TVC.
So the early Starship versions used these heavy hydraulic power units to gimbal the engines around. But the latest generations, they've ripped all that out and replaced it with a fully electric TVC system. This gets rid of heavy fluid reservoirs, it totally eliminates the risk of hydraulic fires, and it provides the millisecond-level precision you need to, catch a falling skyscraper-sized booster from the sky.
So when you put all these pieces together, the 3D printed manifolds, the internal plumbing, the electric actuators, you're not just looking at better parts. You are looking at the birth of an entirely new kind of machine.
I mean, the evolution here is just breathtaking. Fluid power has gone from some 17th century physics principles to the slow, blunt instrument of a post-war steam shovel to something entirely new. It has become a hyper-efficient, featherweight nervous system for our expansion into orbit.
And this whole evolution leaves us with a fascinating final thought. For centuries, we've built machines with brute force muscle. We are now entering an era where we can give them something that's more like a nervous system, one that is intelligent, integrated, and incredibly light. So the question is no longer if we can reach the stars, but what incredible marvels will we build when we finally get there?